Certainly this has been a great meeting, very good setup here, and I want to thank the organizers for their efforts in setting this up and in inviting me here. This will be a pretty short talk. I want to just share a admittedly extremely speculative but fun idea regarding a large black hole recently reported in a relatively small galaxy and how it might have come to be like that. My co-author is Erin Bonning, who is teaching this morning at her brand new job at Emory University just across town here in Atlanta, but she'll be back with us this afternoon. Basically, a galaxy was reported to have a 17 billion solar mass black hole in a paper by Vanden Bosch et al. In Nature in the fall with Carl Gebhardt and a number of others. It is based on stellar dynamics. It is a galaxy that is not much brighter than the Milky Way, maybe a factor of 2. So, you know, the mass of black hole in the Milky Way is 4 million solar masses, give or take. So it's quite unusual. And so I'm going to raise the idea that possibly that black hole got manufactured in a more suitable factory, namely the BCG and the cluster that it lives in, got kicked out, and eventually happened to run into this galaxy and get captured. I don't need to repeat what's already been said, and the people who do it are in the room. We've seen that numerical relativity is now predicting gravitational radiation recoils for the merged black hole up to 5,000 kilometers a second for ideal orientations. And we've had some discussion already about possible ways to observe that, including wandering quasars, as Richard Mushatsky discussed. There is the possibility of detecting these runaway black holes with a certain collection of stars that were sufficiently tightly bound to it at the moment of ejection that they were carried around. And the possibility of black hole migration, which I'm applying today, is not a novel idea. It's been discussed by several authors as regards whether you could see those black holes, such as the Merritt and Camosa proposition, and and the idea of having them recaptured into a black hole, into another galaxy, might, particularly was discussed by Bleck et al., mentioned as a possibility for leading to scatter in the black hole bulge relationship. This is NGC 1277 from the Nature paper. It is a fairly disky galaxy, which will be one possible thorn in my side that we'll mention later on. This other thing off to the side here is, as far as I'm aware, just a background galaxy. You can see, in fact, it comes out pretty well in the projection, a dusty disk near the center, and I'm hoping that that may lead to a possibility of some kind of dynamical confirmation of the mass of this black hole. The black hole is analyzed. You can see the rotation profile and the velocity dispersion profile, which reinforce each other in the Nature paper, and it's basically the rather steep rise in the innermost part of this galaxy based on the HST imaging, and then they have further support with observations from McDonald Observatory to get the dynamical profile and the dark matter profile farther out in the galaxy, which helps to give a more reliable, complete model of the galaxy in a mass-to-light ratio. Basically, they find a black hole of 17 billion solar masses in the center, which is 60% of the mass of the bulge, and it's not a classical bulge, it's a pseudo-bulge. If anything, that makes it even more of an outlier because of recent evidence that pseudobulges have undersized black holes for their luminosity. And I would refer you to the recent annual review article by Cormandy and Ho, which John told me just the other day that they set a record for the length of an annual reviews article, which I readily is like 140 pages or something like that. But there's a lot in it, so there's a very recent source of information. 14%, the black hole is 14% of the total stellar mass. Here is one rendition of the black hole bulge relationship. This is bulge luminosity from this Nature paper, and you can see there is some scatter, and you can see there is some down scatter at the lower luminosities, and I haven't yet double-checked whether some of those are the pseudobulges, but this is very much like the kinds of plots that Cormandy has in the Cormandy and Ho review, where down in that lower left region you have a lot of pseudobulges with undersized black holes, and black holes that don't correlate very well with the luminosity of the pseudobulge. But the point here is, the NGC 1277 here, this lenticular galaxy is, as you can see, a huge outlier, a 2 order of magnitude outlier in the black hole mass versus bulge luminosity relationship. You can also see here that it is not the largest black hole that's been reported. There is a report by McConnell et al. Of a 20 billion solar mass black hole in a gigantic BCG, a CD galaxy in a very large cluster. Of course, there are error bars on these measurements. And so, but you can see that it's quite a substantial outlier. And I recall having discussion of the character of this other outlier. I apologize for not remembering better, but I talked about it with Carl, and I do recall that it did not seem to bear so directly on the discussion that I'm giving today. Here is the Perseus cluster. It's a nearby rich cluster of galaxies. That's at one end of the Perseus-Pisces supercluster. This is NGC 1275, which I'm going to talk about as a possible source galaxy. 1272 is an almost as bright giant elliptical in the cluster. Here is this little guy here is NGC 1277, the object in question. 1278, this larger elliptical, right over here. And what I'm going to focus on in terms of what I think is the best option for an expulsion is to kind of focus on the possibility that it came out of 1277 with a velocity that allowed it to orbit around in this central subcluster. Of course, this probably happened billions of years ago, and exactly what the cluster looked then, one could only guess. So the proposition is that NGC 1275 came together with the aid of a major merger itself. We had a in-spiral, a gravitational radiation recoil event of the type that has been discussed here. The black hole got kicked out at 1,000 kilometers a second or 1,500, wandered around for who knows how long, possibly billions of years, had a chance encounter with this guy. It would have to, as I'll show, have to be a little fortunate in terms of the relative velocities. As many of you know, the velocity dispersion is like 800 kilometers a second in this cluster. So the relative velocity for most collisions is going to be more than the escape velocity from the individual galaxies. So capture requires a certain amount of luck. And so anyway, the proposition is that it had that luck, came in with an impact parameter and a relative velocity that would allow for dynamical friction to capture the black hole and draw it into the center of the galaxy.
Greg, what's the scale on that picture?
Yeah. Well, thank you. That's a good thought. This subcluster here is about 1/4 of a megaparsec across.
So Greg,
I'm sorry?
a postscript to the story is that a new supermassive black hole has been formed in 1275.
Yes, correct. And of course, whether there's any evidence that that's puny for this galaxy will be one of the tests we might like to discuss later on. Believe it or not, thanks to the efforts of people like are in this room, to my mind, the escape part of this fairy tale is less problematic than the capture. And that in itself is, of course, why we're all excited to hear about candidates like Richards, is that you could actually be talking seriously of kicking black holes of billions of solar masses out of galaxies and have them wander around their environment. But we've talked about the fact that black holes like this are around. And so what one might envision, for example, they've now jacked the mass of the black hole in M87. I can hardly keep track, but has it crept up even above 5 billion lately? 5 billion comes to mind, but I think there's been a claim of 7 or so. So we need a pair of those to come together and produce NGC 1275, and then have the merger and the ejection. An escape velocity, if you want to estimate it roughly, Merritt suggests to multiply the sigma star by a factor of 5. NGC 1275 is not a particularly high velocity dispersion galaxies, but these CD galaxies often have luminosities out of proportion to their stellar velocity distribution. So that gives you 1,250 kilometers a second. Well, that is easily within the limits of 5,000 kilometers a second for the maximum kick velocity that is now being reported. The trouble is it takes a kind of a lucky combination of parameters. There has been some evolution. Papers like Campanelli et al. A few years ago found kicks up to 3,000 with the spins lying in the orbital plane of the two black holes and anti-aligned. The work that I read, such as Lusto et al. Here, seem to be finding a somewhat more forgiving range of angles that will still give you a quite large kick. And as I look at their figures for nearly equal masses, about 25% of the parameter space gave an escape velocity large enough for the an ejection of this magnitude. So if it was a reasonably dry merger, And as has been proposed by Tamara and her co-workers, we might kill off these big kicks if gas aligns the black hole spins in a parallel fashion. Accretion of gas onto both black holes might line up the spins in a unoptimal configuration to produce large kicks. So if that process is efficient, then we would have needed to have a dry merger to produce this CD galaxy. Now, it's not terribly dry today, as I'm sure you noticed in the picture. You can see some hints of the gas clouds and with other photographs. This is probably an infalling, rather high velocity foreground cloud or galaxy. But some of you may know that NGC 1275 is the radio source. Perseus A is a powerful radio source. So there is an AGN in there. It seems to be somewhat obscured to optical view in the nucleus. So anyway, that's the thought on the escape. As to the capture, first of all, do you need to run into another galaxy, or can it just take all those stars with it? And the answer is no. For a velocity of a kick like this, you can estimate kind of on the back of the envelope, and it agrees with formulas that Merritt and Formosa paper have, that it would only take about 1% of its mass. This is for reasonable assumptions about the kind of stellar density cusp you have going into the center. So it might have taken some stars with us. Those might be orbiting around. They might be high-velocity stars. A wonderful thing about this stellar entourage, if it could ever be found, for more reasonable black holes ejected from normal galaxies, it might be kind of a globular clustered luminosity of thing. But the beauty of it is that the stars that get carried along are the stars that are bound to the black hole with more than the more than the velocity of the kick. And so they remain orbiting with a velocity that is the order of the kick velocity. So you'd have a much higher velocity dispersion than you would normally have. And not only that, but from that velocity dispersion, you can reconstruct the kick velocity. So it would be really quite fun if you found an example like that. It's worth looking.
And they live forever.
And they live forever. What? I'm sorry.
But we'll discuss.
I'm nearly done, so there's plenty of time if you want to put in a remark. Anyway, we need to recompose the galaxy. Now, often people will remark, wouldn't it be a little less elaborate to just say that you formed this black hole in a giant galaxy and then some kind of encounter stripped away a lot of that galaxy? And I've discussed that with Remco van den Bosch, who has looked at it, but the basic thought is that if you want to have kind of tidal stripping of this galaxy, and NGC 1277 is a fairly compact, dense galaxy, then you need a more massive but also more dense perturbing galaxy to strip it away. And those galaxies don't exist. So I haven't pursued that, and he doesn't seem to think it's a promising idea. So that leaves us with this suggestion of capturing it. I've talked about the velocity dispersion of the cluster. Basically, for a slow encounter and an impact parameter of 10, 20, 30 kiloparsecs, I find using simple Chandrasekhar dynamical friction that you can capture the galaxy. And I've just had a discussion with Jill, who makes me aware of some work, simulations where the Chandrasekhar formula doesn't necessarily nail the actual dispersion, dynamical friction, so I'd love to see some simulations of this kind of a capture process. Meanwhile, taking it at face value, what I find is that if you eject with more than the escape velocity, the probabilities of what the kick velocity are, they ramp down to 0 at 5,000 kilometers a second, but there's a curve which kind of favors things that are not hugely above the 1,250 kilometers a second. And so you've got a decent chance that the object would not get kicked all the way out of the cluster, a majority chance, and that it might well orbit just in that inner subcluster that I showed in the illustration. And that being the case, you can estimate kind of on the back of the envelope. This is not a particularly complicated formula for this meeting. All it is the impact parameter in units of 10 kiloparsecs and the fraction of galaxies that have a velocity at any moment of 300 kilometers a second or less. And that turns out to be about 10 kiloparsecs. And you put it together just with the density of galaxies in that subcluster, and I get a probability of about 10% in the Hubble time that the black hole, if it is kicked out with a velocity that has it cruising around that central cluster, might be captured like this. Well, you put that together with the 25% probability that you get kicked out in the first place, and it's not, it starts to get a little tough. On the other hand, these are rough estimates. I could be more optimistic, but the truth might be more optimistic than I've gotten. The other thing is it's a big universe, and rare things will come to our attention, so you don't want to be too unwilling to think about exotic possibilities. Well, if NGC 1275 kicked out its black hole, should it have no black hole now? Well, this possibility of black hole-less galaxies has, of course, been discussed in the context of kicks. Clearly, it has a black hole because it's an AGN. There are measurements based on molecular gas that suggest a black hole mass of about 3 times 10 to the 8th to 7 times 10 to the 8th. But the latter authors said treat this as an upper limit because of all the molecular gas mass that was within the orbital radius they were studying. That is quite a bit smaller than you would predict from the luminosity of NGC 1275. And with these large galaxies, the evidence is that the black holes for BCGs, trace the luminosity rather than the sigma star. Of course, there's evidence that when you get into BCGs, the Faber-Jackson relationship fails, and they tend to level off in sigma star. So maybe it would be nice, and I've heard rumors that people are trying to get a better mass for that object, so that would be interesting to see. But in any case, assuming this event happened billions of years ago, there are going to be some more galaxies merge in with the BCG. They will bring black holes. You'll also have accretion. In fact, it's going on right now because we have the AGN. So, it may be just what you would expect, that it is a smallish but non-zero black hole in NGC 1275 today. Now, if you have a major merger and the two black holes come together, it has been proposed by Merritt and others that you would scour out a core in the center, meaning that you would kick the stars out of the very center, and the normal cusp of increasing stellar light and stellar density would be shaved off. So you might expect a large core. Well, this has not been an object, 1275, that has been part of the Weber et al. Study of objects, probably because it is a messy system. And so I think it's unclear now whether it has a core. And yet, remarks are in the literature that it should be fairly easy to refill a core with some billions of years of more minor mergers going on in stellar dynamics. So maybe that, unfortunately, isn't even an ironclad test. By the way, there is, sorry that I forget the name, but there is a BCG which has been claimed in a paper by Lauer and company just a year ago that has a huge core and no black hole. And so they threw out the possibility, independently of what I'm doing here, that that was a case of ejection of the black hole. And so that would be an interesting thing to see if that would be a multi-billion solar mass black hole. There's evidence it's kicking around somewhere. And I've already mentioned this final parsec issue. And we know now that the final parsec problem is not a problem, although I'm hoping for a dry merger here, so that gets rid of maybe the best way to get through the final parsec, but we have been told as long as there's triaxiality or something. So I'm not too worried about that. Honestly, I don't know, others may disagree. My feeling is that if there were a lot of 1 parsec supermassive binaries in galaxies everywhere, we would know it. All right, as to 1277, well, it's a pretty disky galaxy. I mean, it's not a spiral galaxy. It's classified as an S0. Can you bring in a black hole that is 15% of the total stellar mass, have it merge to the center, and not heat up that galaxy enough to produce and get rid of that disk? So we need a simulation of that to see whether you can do it, and not produce a core. They claim it has only a pseudo-bulge. Would you not have more classical bulge than we see? I can't address that quantitatively, but I imagine with the tools that people have these days, it shouldn't be too hard to make a simulation of this kind of capture. On the other hand, the angular momentum that you would bring into the collision for a typical impact parameter would be of the same magnitude as the rotation of the galaxy today. So normally we talk about mergers as kind of heating up galaxies and destroying disks, but I wonder if the angular momentum coming in could also have some effect on the final morphology of the capturing galaxy. For the normal kind of black hole time, if this happened billions of years ago, the black hole in spiral time, it should be pretty easy to get it to settle to the center, but again, there may be a question of how precisely centered it is now. So that may be something to study. One thing about this object, and there's a Fabian et al. Paper, they were very nimble, they got that out in a month after the Bosch et al. Paper, mainly talking about the X-ray emission from the hot gas in the cluster, because Fabian had already studied to death, you know, about the X-ray waves and all that, and shells that have been studied. And so they had the data, this object, 1277 was in it. But they do make an interesting theoretical discussion, which is just to point out, if it grew by luminous accretion, you know, that's a solar mass a year over the Hubble time, which is a 3C273 luminosity for normal accretion efficiencies. And it's a pretty nearby galaxy, so you get too many at the back of the envelope level, you get too many 3C273 level quasars in space and over the history of the universe if this thing grew by luminous accretion. You can ease that if it largely got put together by mergers of black holes that started out smaller. If there are too many of these objects around, then you collide with the issue of, it took some luck. If my estimates are right, it's going to be a few percent probability. So if more of these are found, it may, and particularly if they occur outside clusters where there's no obvious source for the giant black hole, that would suggest that you can make these things in other ways, and then you might invoke Occam's razor to wonder whether we want to throw our weight behind this scenario for this object. On the other hand, it's a big universe. There are a lot of clusters out there, and so if the probabilities are really a few percent that a BCG in a large cluster of galaxies would do this, then there must be, scads of examples of this kind of migration in clusters that are within the reach of our telescopes, and so that might be interesting to look for such examples. Thank you.